So our goal today is to take a look at what polynomial graphs look like, how we could have an idea of what the polynomial graph looks like without just punching it into our graphing calculator. And so the key is going to be looking at the leading coefficient and the degree, whether the degree is even or odd, and whether or not there's a negative out front in the leading coefficient. It's going to tell us the rough shape of the graph. Right? And so all the even degree things, x to the fourth, x to the sixth, x to the eighth, are going to look like x squared. And in fact, if we do just have y equals x to the fourth, if we don't have any kind of extra terms, it's going to look almost identical, just a little bit steeper, but it's just going to basically look like a parabola. The higher the exponent, the kind of steeper or narrower it'll be, but it's just going to look like this. Same thing for all these odd degrees here. It's just going to look like our basic x cubed. Higher exponent, it's going to be a little bit steeper, a little bit narrower, but it's just going to look like that. Now, if we do have extra terms, then it can create extra turns in the graph. So this x to the fifth graph right here, it could still just look like this. It might not have any turns, but it might have a few turns. It might look something like this, or it might look something like that. Because of these extra terms in the polynomial, we might have these extra turns in the graph, or extrema. Extrema means maxes or mins. So these turns could also be thought of as relative maxes or mins. And so if we have those extra terms, we could get those, we might not. Okay, this negative 7x to the fourth, it might just look like a negative x squared. It might just look like a parabola opening down. Or, because there are extra terms in the polynomial, we might have some extra turns in the graph. Okay, but regardless, we know what we're going to call the end behavior is. We know what direction the arrows are going. If I kind of cover that middle of the graph up right there, those all look the same. The arrows are pointing the same direction. If we ignore what's happening in the middle of the graphs look the same. The arrows point the same direction. And so that's what this chart here is going to tell us. Based on the degree and whether it's positive or negative, we know the end behavior, we know the arrows. Okay, and so this shouldn't be anything new that you have to memorize. You can always go back to something that you know. So even degree, positive leading coefficient, we know x squared. And so we know that the ends of the graph are going to look like this, like a parabola. Okay. Now, if it's x to the fourth, x to the sixth, and they have some extra terms in the graph, or in the polynomial, there might be some weird stuff going on in the middle. There might be some extra turns. We don't know what's going on in the middle of the graph, but we do know if the degree is even and it's positive leading coefficient, that the arrows at the end behavior, is going to look like that. And then, of course, if it's negative x squared, then it's going to look like that. Maybe some middle funny stuff if we had higher degrees and more terms, but the ends, the arrows will look like that. Okay, odd degree. So hopefully you know what x cubed looks like. If you ever forgot, though, you could also think about just y equals x. Y equals x, a positive slope line, is going to go this direction. So this arrow is going to go that way, and then that arrow is going to go that way. Okay? And then depending on what we actually have, there might be some funny middle stuff going on here. And then here you could think about negative x cubed, negative x to the fifth. If you had a line with a negative slope, downhill line would look like this. The arrows will go those directions there. Or if you know what negative x cubed looks like. Again, just tells us the end behavior of the arrows. We don't know what's going on in the middle. Okay. Now notice I only gave a few specific possibilities here of how many turns, how many extrema could have possibly been in the graph. There's actually a rule for it. It's the degree minus 1. We also know that the maximum number of zeros or solutions or x-intercepts is equal to the degree. Again, if you don't want to memorize this rule, go back to something that you know. Think about x squared. Well, x squared, that's a parabola. Well, how many turns does a parabola have? A parabola only has one turn. It only has one either maximum or minimum. And then think about how many solutions you could have. Well, x squared, you're used to thinking of two solutions. Of course, it's not always two solutions, though. Could be one solution, could be no solutions. Okay? So two solutions, one solution, or zero solutions would be the possibilities. And so that's why we say it's a maximum number of zeros. If you have a degree of 2, the most solutions you could have is 2. You could have less. Okay? But if you think back to x squared, you'll think, okay, the solutions goes with the degrees, and then the number of turns, oh yeah, that's one less than the degree there. Okay? And again, it's a maximum number of turns. X to the fifth might only have this one turn here, or zero turns actually on this one. Could have zero turns, could have 2, could have 4. It's a maximum number. Right? So here, the maximum number of zeros, that's just the degree, 5. And then the maximum number of turns, that was this one that I drew here, only 4, one less than the degree. And then on this one, maximum number of zeros, equal to the degree, maximum number of turns, one less than the degree. All right, so now let's try to actually graph some of these things, and then we'll see how close we get with our compared to our graphing calculator. So we're going to actually find the zeros. So x cubed, so I'm going to be looking to see if I can find 3 zeros. Maybe not, it's a maximum number, but that's the most that I could find. So I've set it equal to 0. Zeros are the x-intercepts. We want the y to be 0. Got a GCF of x, so we're factoring that out. Then factor the quadratic that's left. And so we get x equals 0, 3, and -2. Okay, so I'll plot those x-intercepts. All right, then I need to draw the polynomial through these. Well, remember, look at this leading term right here. We've got a degree of 3 and a positive leading coefficient. So I know that the arrows have to look like that. X cubed is just like x to the first. It's like positive slope, uphill line at the ends. And so down here has to go like that. And then we can just kind of cross through, and then that makes the other end go like that as well. Okay, so now why don't you go ahead and try number 2. Now number 2 is a little bit trickier. So on this one, I just went cross through. On number 2, they're not all going to cross through. So make sure maybe do the arrows at the ends first, and then see if you have any idea. If you get stuck on how to, one of them doesn't cross through, normally in Algebra 2, there's something you would have talked about. You might not have talked about it in this past spring, but go ahead and give number 2 a try. Actually, let me go ahead and real quick, let's just compare the graph on the graphing calculator with how we did. So it looks pretty close, right? Very similar, very close. The one thing you might think, oh, we didn't really do this part very good. The one part that's not matching that great, we didn't really know where the relative minimum and relative maximum were, right? This minimum down here kind of went a lot lower than we had on our graph. So really, if we could find the minimum and maximum without a calculator, then we could really do almost a perfect graph without the calculator, right? Well, stick around for AP Calculus next year. In AP Calculus next year, you'll be able to find what these minimums and maximums are without a calculator. All right, but for us, as long as we get something kind of rough sketch like that, that'll be enough. So you go ahead and give this second one a try. Just maybe do it in pencil or something like that, because there's one tricky thing you might have a little bit of trouble with. All right, so here's what this one looked like. So the tricky thing is, we know that the arrows at the end have to go this way, but if we just went cross, 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 we'd have the arrows going in the wrong direction, or cross, 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 the arrows would be in the wrong direction there. The reason is there's something called a double root here. So normally this would have been talked about a bit in Algebra 2. So because there's this squared on the x, it's like the x is happening twice. Right? X squared, of course, is x times x. So you're getting the factor x showing up twice. So it's a double root. It's like this root is happening twice. And because of that, it just touches on the graph here. It doesn't actually cross through. It just touches. All right, and so that's how that graph is going to look. Now, this idea of a double root, actually in general, we can take a look at kind of any kind of repeated zero. So anytime we have an exponent on a factor of the polynomial, it's called a repeated zero, and the exponent is called the multiplicity. Okay, so on this example that we just looked at here, this was a multiplicity of 2. A factor had an exponent, so multiplicity 2 for a double root. And based on the multiplicity, we know whether the graph is going to cross or not. So that was the issue. We might not have quite been sure how to graph that because you weren't sure which ones crossed, which ones didn't. Well, now we're going to know. We're going to know if there's an even exponent, it's not going to cross. Okay, and again, you can always go back to what you know. You know, if you've got just y equals x squared, well, at the 0, 0, it doesn't cross right there. It just touches the x-axis. And then odd multiplicity, again, think about something that you know, y equals x cubed, it does cross through the x-axis right there. Okay, so let's take a look at this here. So we're going to give it to you in the factored form. That should help you out a little bit. In terms of the zeros, now for the degree, you're going to have to do a little bit more work. So you're going to have to think about, if I multiply this out, don't actually do all the multiplication. don't do all that work, but think about if you multiplied it out, what would be the degree? What would be the leading coefficient? What would be that first term right there? And so what would be important would just be the highest exponent parts of it. You could delete this constant, ignore that. You just want the negative x cubed times the x squared. Don't sweat the small stuff. Just ignore the constants and then figure out these higher order, higher power terms. And so we're going to be getting negative x to the 5th. And so that tells me that it's going to be that kind of shape and that my degree is 5. Okay, negative x to the 5th, like negative x cubed, like just negative x, like the downhill line. All right, and so then we've got x equals 0, right here is our 0 right there. And then x equals 2 right here. And we want their multiplicities. The multiplicity is just the exponent on the factor. So this one is multiplicity 3, and this one is multiplicity 2. And that's going to tell us whether or not they cross. So this graph at one of the solutions is going to cross, and at one is not going to. And so this 2, that's the double root. This one has an even multiplicity. So this one is just going to touch the x-axis. It's not going to cross. With an odd multiplicity, it is going to cross through. So when I go to graph this right here, I've got 0 at 0, and then the 0 at x equals 2. And then I know my arrows have to go like this and like this. And then we said at this one, it's going to cross. And then at that one, it's just going to touch. It's not going to cross. On this one here, be careful with these backward subtraction ones. There's a negative on the x there. So this is negative x to the 5th times x. Now, if you have negative x to the 5th, is that negative still going to be there? Is it going to go away? It is still going to be there because it's an odd exponent, right? If that was an even exponent, if that was negative x to the 6th, then the negative would just disappear. But it is going to be negative x to the 5th times x. So negative x to the 6th. So that's like negative x squared. It's going to look like that. We've got a degree of 6. Okay. And so let's take a look at these zeros here. We've got x equals 1 with a multiplicity of 5. That's odd. So the graph is going to cross right there. And then we've got x equals -4. Now this one, there's no exponent there, so I mean technically it's not even a repeated 0. You could talk about the multiplicity though. You can always put an exponent of 1 on something, so you could just call it a multiplicity of 1. Now it's not even a repeated 0, so it has to be normal. It has to just cross through the x-axis. All right, so we've got a 0 over there. 1, 2, 3, 4. One other thing you could find if you wanted a really nice graph, the y-intercept is another nice point to look at sometimes, like especially if you're doing matching. Sometimes when you're doing matching, looking for the y-intercept can be an easy point to find here. You could just plug in 0. You can see pretty easily the y-intercept would be at 0, 4. Okay. All right, so the overall shape is like a -x squared, -x to the 6th, like -x squared. So it's going to look like that. Okay. And then let's see, we said at both of these it's going to cross. So it's just going to go like this and then like that. Right. Now it's not necessarily just like that. It could have some extra turns. It could look something like that, with some extra relative extrema in there. It could have more. It could have up to, how many here? 5, right? So there might even be a few more squiggles in there. But again, we need AP Calculus to figure out what kind of relative extrema it has. For us, as long as you've got the zeros behavior correct and the arrows at the end correct, we're going to be happy. So why don't you go ahead and try numbers 3 and 4 there. Right, so your graph should have looked something like this. And again, if you had more turns in there, you could just don't put too many turns in there, right? There is a limit to how many turns it could have. But on this one here, we had the x to the 6th parabola-like shape at the end there. Again, cover up the middle, and it just looks like a parabola at the ends there. The multiplicities told us which ones crossed, which one touched. Now take a look at your number 4. See if you got number 4 right. Number 4 is one that tricks people a lot here. So we had -x cubed and then -x to the 4th. So on the odd exponent, 3 negatives is still negative. The even exponent, 4 negatives cancel out, and that one was positive. So negative times positive, this one did have a negative leading coefficient here if you multiplied it all out. So it was a -x to the 7th. That one tricks people a lot of the time. So take a look at that. If you had the shape going the other way, double check that work there of how we multiply this out. Watch out for what kind of exponent you have on those negatives right there. Okay. So one last thing here, let's try to actually find the equation. Let's try to go backwards. Let's say we've got the zeros, we want the equation. So we did this a little bit with quadratics in the previous lesson. So the idea was if you have x equals 5, you know what you had as a factor. You had to have x minus 5 as a factor. If you have x equals -1, you had to have x plus 1 as a factor. And then x equals 0 goes with just x as a factor. So then we'll have x times this quadratic here, x squared minus 4x minus 5. And then distribute your x through. So we've got x cubed minus 4x squared minus 5x, and it's set an equation, so we should call it y equals. Okay. Notice these directions about a leading coefficient of 1. That just means don't stick like pi in front of this. Don't stick a negative. Again, you could have, if we didn't say that, you could have different leading coefficients out here and still have the same zeros. So we're putting this in here to make sure there's only one answer. And then the standard form is what told us we had to multiply this out. Now here's the one that's a little bit trickier here. Okay, so x equals 3. We're going to have x minus 3. And then for this, okay, we need x minus 5 minus root 2. And then x minus 5 plus root 2. Because what we have to do is x minus 5 plus root 2, and then x minus 5 minus root 2. And so the minus gets distributed to the 0. Minus 5 plus root 2, distribute the negative. You're both negative here. Minus, and then 5 minus root 2, distribute the negative, negative. This one changes to positive right there. All right, now here's the key to actually being able to multiply this out here. You've got to, first of all, do these two together first, and then group it a certain way. The key is to see a minus here and a plus there. So we're going to group the x minus 5 and then the root 2 separately, the x minus 5 and the root 2 separately. So what we've got is actually a minus b and then a plus b. We've actually got difference of squares. We can write this as a squared minus b squared. We're going to have this x minus 5 was the a. We're going to have x minus 5 squared. And then b was the root 2, so minus root 2 squared. And so that's what we're going to get for this first multiplication part here. The x minus 3 is going to hang out for a little bit. So we're going to have x minus 3 times, this is x squared minus 10x plus 25, perfect square pattern, x minus 5 times x minus 5. And then root 2 squared is 2. So x minus 3 times, this is x squared minus 10x plus 23. And then here, distribute your x through and then distribute the negative 3. So distribute the x through, I'll have x cubed minus 10x squared plus 23x. And then when I distribute the negative 3 through, I like to line up my like terms. So negative 3 times x squared, I'm going to put the negative 3x squared down there. Lines up my like terms for me. And then plus 30x and minus 69. And so then I can combine those like terms. X cubed minus 13x squared plus 53x minus 69. And it did say an equation, so I should say maybe y equals here. All right, and there's our answer. Y equals x cubed minus 13x plus 53x minus 69. Now, if you didn't like this little difference of squares trick here, there is another way that you could look at this. You could say, all right, we had x equals 5 plus or minus root 2. And so you could kind of try to walk backwards what your solution steps would have been. So if you ended up with this, well, what you would have had before that was x minus 5 was plus or minus root 2 because you added a 5 over to the right side. And then, well, how did you get that plus or minus? Well, you square rooted, which means that you had to have had a squared right there. And what do you square root to get the square root of 2? Well, you square root 2. So then we could square this out. X squared minus 10x plus 25 is 2. And then your goal would be to get this equal to 0. The factors have to be something that equals 0 to give you the solutions. And so subtract the 2. X squared minus 10x plus 23 is 0. And then you would be up to that step right there. So a little bit tricky here when you have these kind of ugly zeros that you're working with. Either do this funny multiplication with a different squares pattern or kind of work your way backwards through the solution process here and then multiply it by the other factor.